Welcome back to Physics Fundamentals. In this video, we're going to be adding vectors. Remember from our previous study, the concept of a scalar measurement which is a measurement which has some magnitude, and a vector measurement. A measurement which has a magnitude and a direction. Vectors are the measurements for which positive and negative, forward and backwards make sense, have some physical meaning. Things like time, mass, and density are scalar values. Things like position, velocity, and force are vector values. So we have, by and large, been dealing with vectors that stay in one dimension. We had some force moving us to the left and some other force moving us to the right. If we really wanted to get creative, we talked about a couple of situations where we also had a force moving us upward or downward. And we talked about the fact that you could look at the vertical components and the horizontal bits on their own. You could look at the normal force and the force of gravity and ensure that the object wasn't going to go up or down. You could look at the friction and the applied force and figure out what was happening with the object trying to move left or right. But what if things aren't that simple? What if you have one force that is trying to move kind of off in this direction? You have one that's trying to move off in that direction, and one that's trying to move up in this direction. First of all, a little bit of vocabulary here. The resultant is the vector solution to vector addition or subtraction. I'm going to not get as far as having three vectors all at once. Having just two vectors, I think, is going to be complicated enough. The next thing we need to do is establish some notation, some convention for describing the direction that a vector is pointing. And so mathematicians invented a concept known as standard position. If we go to a normal coordinate plane, x-axis going to the right, y-axis going upward, a vector in standard position starts at the origin and goes off in some way, shape, or form. We call the starting point of the vector its tail, and we call the ending point of the vector its head. And the angle of the vector is always measured in the counterclockwise direction starting at the x-axis. So if I have a vector which is 3.5 centimeters at 53 degrees, well, 53 degrees is an angle about that, and then measure along that line a distance of 3.5 centimeters. If I have an angle of 100, I'm sorry, I'm saying this backwards. if I have a vector that is 4.2 centimeters at 111 degrees, well, from standard position, an angle of 111 degrees takes us about to there. Then along that line, I go a distance of 4.2 centimeters. When it comes to adding vectors, the picture of adding vectors is what we call head-tail addition. So if I have, let's say, 3.5 centimeters at 75 degrees, and I want to add to that 2.8 centimeters at 175 degrees, well, the way I'm going to set this up, I'm going to draw a very small set of coordinate axes at some origin. I'm going to measure out my 75-degree angle, and then I'm going to go along that angle a distance of 3.5 centimeters. Then, at the head of that vector, I'm going to sketch out another set of coordinate axes. I'm going to measure out my 175-degree angle, and I'm going to travel along that direction a distance of 2.8 centimeters. The resultant vector is the vector which points from the tail of the first one to the head of the second one. So if you think about this as, well, these are small measurements, so driving directions for an ant. The ant starts off going one way, then turns and goes another way, and the resultant vector is the straight line path that gets us to the same place at the end of the navigation. If I have a large enough page to work on, and I have a high quality ruler and protractor, I can simply draw these vectors and measure out the result. It absolutely works, and there's nothing wrong with it, except that it's annoying. It is a very tedious process to do, and it's a very difficult process to do with any sort of precision. So luckily for us, that's actually not the best way to go about trying to find the resultant vector for angle addition. The other approach is what's known as the components approach. To make sense of the components approach, let's come back up here to one of the earlier vectors we drew. Now that I know how vector addition works, I can break any vector into components. I can start by traveling directly along the x-axis until I get to the point where I can make a break for it and travel directly perpendicularly to the x-axis and form a right triangle. Now wait a second. This is a right triangle that has a known angle and a known hypotenuse. Triangle trigonometry can let us know what these components are. So if I have a vector that is 3.5 centimeters at 75 degrees, I'm not going to use any sorts of tools. I'm just going to roughly approximate what 3.5 centimeters at 75 degrees looks like. And then I can use triangle trigonometry. Let's go ahead and give this thing some names. Generally speaking, if we're talking about a vector in 2 dimensions, we're going to use letters like U and V. We'll also use R and S occasionally. But to indicate that this variable is a vector and not just a numerical value, that is, it has an angle attached to it, we're going to put this little harpoon or hat on the vector. It's just a notation to remind ourselves that this thing is something a little bit different. The component of the vector along the x direction is not a vector, so it's not going to get a hat, and it's going to get a subscript of x. And then the vertical component will get a subscript of y. Right. Trigonometry. If I take Vx over the hypotenuse, 3.5 centimeters, that is the adjacent side of the triangle divided by the hypotenuse, and the relationship between adjacent and hypotenuse is cosine of the angle. My calculator is very happy to tell me that 3.5 times the cosine of 75 is 0. I guess I'll round that to 0.91. And I'm running a little bit low on space. I can just scroll this down a little bit. I can do the same sort of thing for the y component. Vy over 3.5 centimeters. That's the opposite leg divided by the hypotenuse, and the relationship between opposite and hypotenuse is sine. Punch that into my calculator, and I get that Vy is 3.4 centimeters. This pattern is fairly common. You will see a lot of sources that tell you that you should just memorize that Vx is V times the cosine of theta, and Vy is V times the sine of theta. I wanted to mention this in case you have come across a physics course or an engineering course where you've used these sorts of things before, or you've studied enough mathematics that you've learned those formulas in mathematics. But I also want to stress that they're not foolproof, because they rely on the angle being given to us in standard position. And a lot of times it is, but every now and then it's not. Every now and then you get a weird angle, and it turns out that the angle you're given is this one up here instead. So pay attention to the triangle. Always draw the triangle and follow the rules of triangle trigonometry. That way you don't get fooled the way that you can be with those sorts of measurements. Whoops, that's not where I want to go. I wanted to scroll up here. So I figured out that one angle, 3.5 centimeters at 75 degrees. So one way we can write this whole thing together, when you have a vector given as components, a lot of times you'll see these angle bracket notation. So you put the x component 0.91 and the y component 3.4. And we use angle brackets instead of parentheses to emphasize that this is a vector, not just a point, but it's the same XY ordered pairs that you learned how to deal with when you learned about graphing in your study of mathematics. Let's go ahead and take a look at this second vector. And just to give it a name, we'll call it vector u. I'm not going to go through the derivation again. It's going to follow the same format because this is an angle given in standard position. But ux is going to be 2.8 times the cosine of 175, which comes out at, oddly enough, negative 2.8 centimeters. It feels like that's just the same value. And it mostly is. 175 degrees is almost entirely straight across. So with the two significant digits that we have here, that's basically the whole thing. But we can figure out uy by taking 2.8 times the sine of 175. My calculator tells me that that's 0.24 centimeters. So vector u in components is negative 2.8, 0.24. Now, if I scroll back up and borrow that value of v that I figured out just a few moments ago, now that I have my vectors broken down into components, now I can go back to that heuristic rule that we used previously. If you think about the components, what's happening horizontally and what's happening vertically don't really have anything to do with each other. So, if you want to add u plus v, the resultant vector here, you just add the components. Negative 2.8 plus 0.91 is negative 1.9, rounding to the nearest tenth, which is the worst precision that I have. 3.4 plus 0.24 is 3.6. Again, rounding to the nearest tenth of a centimeter, which is the best precision that I have. And that is all there is to finding the resultant. Add the x components, add the y components. Except that's kind of an odd way of writing it, isn't it? When we were given our initial vector, we were given a magnitude and a direction. That's not what we have now. But that's something we can, once again, figure out using triangle trigonometry. The magnitude of the vector is the hypotenuse of the right triangle. Let's write this in, well, you'll notice that I was lazy here. I did not write the negative with 1.9 because I know that positive 1.9 squared or negative 1.9 squared comes out to the same thing. And if I don't worry about the negative, then I'm not going to make any mistakes with my calculator. right, but I get that c squared is 16, which means that c itself is 4.0. And then I can figure out the angle. My known sides are the two legs, so I guess that means I'm going to be using tangent in this case. Tangent is opposite over adjacent. And I need the inverse tangent, the angle whose tangent is 3.6 over 1.9. My calculator tells me that that angle is, I guess I have two significant figures, I'll call it 62 degrees. But unfortunately, that's not actually the angle we want. Because as I emphasized in this picture, well, my x component is a negative value, which means that if I extended out my coordinate axes, I'm over here in the second quadrant. An angle in standard position is measured that way. If I go all the way from the positive x-axis to the negative x-axis, that full distance is 180 degrees. I didn't make it the whole way because the last 62 degrees are taken up inside the triangle I drew, but that means that 118 degrees is what I need in order to get to that red line. My resultant vector as a magnitude and direction is 4.0 centimeters at 118 degrees. All right. So it's a little bit of a different way of thinking about things. Requires you to kind of stretch your mind a little bit, start picturing things in 2 dimensions, or getting used to writing things down. This idea at the end of, well, the angle that's in the triangle is not actually the angle in standard position, we need to do a little bit more, is known as reference angles. And in mathematics courses, you very often will be told you need to memorize that when you are in this quadrant and you have this reference angle, here's the formula. I find that trying to get students to memorize that just causes more confusion than anything else. So my recommendation is to not memorize it. My recommendation is to draw the picture and figure out what the angle needs to be just by knowing that 90 degrees takes you to the first, from the x-axis to the y-axis. 180 degrees takes you to the negative x-axis. Another 90 would be 270 to the negative y-axis. And 360 degrees is all the way around the circle. Right. With that, I think that's all that I need to talk about here. That's all I have time for here. So thank you as always for joining me, and I'll see you again in the next video.